Hi everyone, and thank you very much for the opportunity to explain what we are doing at NetCarbon and how we rely on Dask, how we rely on Coiled. So during this presentation, I'm going to quickly explain what we are doing at NetCarbon, obviously. But after, as you say, Hadi, I'm going to explain the good and bad of Dask, of Coiled, and how it's like matching what we really need in Earth observation domain, and how there is some gap and some stuff to improve in the future, and how to be aware of everything at the beginning of your journey in the Earth observation domain or in the big data domain. So mainly what we are doing at NetCarbon, it's measuring carbon. So the purpose of NetCarbon is to see the carbon to change the climate. As we all know, we have to fight against climate change. And one way, obviously, to fight against climate change is to be able to measure, improve the good KPI in order to fight against it. And carbon is one of the best. So very quickly, who I am. So I am the CTO of NetCarbon. I'm mainly working on Earth observation domain, big data and AI. Here, the most important is like the Earth observation domain, because as we know, the EO domain is like a lot related with big data because we do not have the choice. We are mainly dealing with a lot of data, so at the end we have to be prepared to how to manage these huge amount of data. And the other fact is like you have to be able at the end to use a bit of AI, because as I said, like you have a lot of data and it's very like time consuming to go through all the picture, all the images. So usually you rely on AI or you rely on ML in order to really like find the gap to process all this data. So NetCarbon is part of the Pangeo community. So it's a community that is like helping to deploy like open source tool in order to process big data geoscience, so geospatial data in the world of big data. And I'm pleased to tell you that if you want to join, if you want some more information about Pangeo, I will be pleased to answer any question. The two other facts is like NetCarbon is relying a lot on STAC. STAC is a way to store and to manage Earth observation data, and we will dive a bit on STAC after. And we are the winner of the Copernicus Challenge from Planet. Planet is a Earth observation company in the US, and we rely a lot on the Planet data in order to really measure carbon. So let's dive a bit on what we are doing at NetCarbon. Even if that's not the purpose of this presentation, it's important to understand why we are using this Earth observation data. So as we all know, we have to fight against climate change. And in order to fight against climate change, we have obviously to reduce CO2 emission, and we have to increase carbon sequestration. It's important to rely on key number and on key factor, on key facts, in order to really like find a way to improve carbon sequestration at the right place, with the right tool, with for example, at the right moment. That's why we are developing a technology based on satellite imagery in order to first measure CO2, carbon sequestration. So that's the first step. We are relying on the Earth observation data. Mainly, we are relying on Copernicus data, so Sentinel-2 and PlanetScope imagery. So that's two types of imagery. One, which is like very high radiometric quality. So the pixel is like, the quality of the pixel is very good. And the other is like the revisit. You can have, we are using one image every day in order to really have a good understanding of carbon sequestration. The second fact, sorry, is artificial intelligence. We rely on AI in order to, as I said, improve by the right tool at the right place carbon sequestration. So it's important to measure and after to optimize and to improve this potential of storing CO2 from the atmosphere to the biomass to the soil. So that's like the technology with our processing and what we are doing at NetCarbon. So measuring carbon and after improving and finding some way to store more CO2. And after what and how we are doing it, mostly is based on data. And here it's a small example on how you are able to process this data and how you are able to really like find the relevant insights, compute it at scale, and after to be able to load it, to be able to save it, and to be able after to deploy some solution based on the data that you already have. So here, what I really want to show you, it's that Earth observation data is mostly exactly the same than every other data, but the huge gap is really in the transform step. So here we have to extract this data. Mainly, we are using STAC, which is like the relevant tool to find the good data at with the relevant. For example, you want a specific date, you want a specific area. So it's allowing people to find the relevant data. And after you will transform this data, and here it's why we rely on Dask and why we rely on Coiled is mainly to be able to compute data at scale without the need to really like dive hour and hour on all the infrastructure. We just want at the end our KPI. We just want at the end to be able to measure CO2, to measure carbon sequestration, and to deploy solution. So the heart of NetCarbon is really like the processing, but not how to scale the processing. We really like we are really relying on the Dask and Coiled to be able to process those type of data. And after the last step, so when you have extracted data, you have transformed the data, you have to be able to load, obviously, the data and to store it, or you can store it directly in a database like Postgre, or you can store it in BigQuery, or even there is a lot more possibilities. But at the end, the idea is to be able to store it and to build some API based on this data, for example. So here, it's how to manage to do some insight at scale and how we manage to do some of these insights at NetCarbon. And here it's like the more important part, obviously, is how we are using it today. And a small example of how Coiled and how Dask is helpful for Earth observation domain. And at the end, we will move to the pro and cons part. Okay, so let's go. It's the Jupyter Notebook. So the main idea is to do something which is easy to interact with the data. It's easy to understand the data, and at the end you will be able to store the data. And when your pipeline will be built, you will be obviously able to convert it to a Python script directly and to run it. Usually, you will run it directly as a Python script and not as a notebook. But for the purpose of this presentation, it's obviously better to use a notebook to be able to really like dive on each part of the code. So here I've tried to be extremely like I'm going to be clear as I can. So the most important part is these parts, so GeoPanda, Shapely, planetary computer, and after we will use Coiled to be able to run everything at scale. So the first step is obviously to import the data, nothing new. After, as I said, you have the PyStack here. PyStack is a way to find the relevant data for your purposes. So for example, here you have an API, a Microsoft Planetary Computer API. This API is like allowing people to be able to search for Earth observation data. So here I'm going to search for some data, just to script to search from Landsat A data. So Landsat A, it's a satellite which is a satellite from the NASA. It's totally open data, so everyone here is able to search for this data, to find some new indexes on this data, and to compute maybe some new insights for anyone. And after, here we have two important Python functions. Obviously, the first one here, it's create cluster. So here is the part that we are really relying at NetCarbon is Coiled, obviously. And why we are relying on Coiled, it's mainly because here I'm doing all this computation, not on my own computer. It will not fit in my computer. So I want to be able to compute this data, but I'm not going to manage everything, all the infrastructure stuff. So instead of spending a lot of time and resources on the way to construct the good infrastructure, I'm just relying on Coiled to construct this capacity, this infrastructure for me. And it's pretty simple, even if there is obviously some difficulties at the beginning, and we will speak about these difficulties after, but here in the script is extremely simple. What I'm doing is just like these 4 lines are important. The first one is here, I'm just saying that I want a cluster from Coiled. I want 4 workers, and so 4 computers, let's say. And after, for each of these computers, I want a certain amount of gigabytes. And I can change it as I need, as I want. So for example, if I need like 8 computers, if I want 1,000 computers, I can change it without any issue. And the part which is important is the software, because as you are not going to run this code directly on your computer, you are going to run this code on a remote computer managed by Coiled and Dask. So you will need some libraries, and you have built a software which is pre-built and which you are able to change easily based on the Coiled documentation. So here I'm using a software where there is some libraries, some basic libraries, for example, Rio XArray, STAC, GeoPanda, and XArray. So that's some library that I need for my computation that are, for example, XArray is based on Dask, so I'm able to manage everything without any issue. The second line is important also. It's because when you are dealing with Earth observation data, but not only with Earth observation data, you are not sure of how many gigabytes you will and worker you will need at the end to be able to compute everything. So you really want to have something which is able to scale easily. And this small function is helping you to scale. So here is just saying that if I have nothing to do, like the minimum of worker will be 2, so I will reduce the cluster. And if I really need power, I will go up to 12 worker. But I can change it, obviously. I can move it to 1 and go to 1,000, etc. And after, when I have my cluster, so I have defined my cluster, I know what I really want for my cluster. I just have to connect Dask and the cluster. And that's it. So what are we going to do with the data? So it's important, obviously, to retrieve the data, extract, and as we say after, we are going to transform the data. So what we're going to do is computing the land surface temperature. So basically, when the satellite is passing through some places, he has some different bands, so he's able to see different colors. The satellite is able to see the blue, the red, etc. But the satellite is also able to see the temperature. So that's something which is very important. This is only possible with Landsat 8, Site 8, Landsat 9, but just with Landsat data. So you are able to retrieve the temperature, and with this data, you are able to retrieve exactly location where the temperature is higher, location where the temperature is less than the usual one, for example. So we are going to compute this land surface temperature to be able really to dive on some like new insights based on the satellite imagery. So here it's some parameter. Some parameters. So the main idea is just to know that I want to search from specific location. So I'm going to search for Paris location, and this is just the ID of Paris in our database. But obviously you are able just to instead of using API and stuff like this, you are just able, for example, to run GeoPanda and open a file with GeoPanda, and actually it will directly show you the data that you need. So, okay. The first step is to be able to import all the libraries to be able to compute your insights. After, you will have obviously to connect satellite imagery, so Landsat 8, for example, Sentinel-2, etc., etc. You will find a location. You will like give a location. Here it's Paris, so it's the place that we are going to study. So we are here. So basically, we are not based in Paris. We are based in Bordeaux. But for the purpose of this session, I think Paris is like well known compared to Bordeaux. So here we are in Paris, and that's the area that we are going to study during this presentation. So the first step is to retrieve all the data. So I'm just using this function, the Landsat 8 function, to be able to search for the data. So here it's some stuff that we have done directly at NetCarbon, to be able to connect to the planetary computer API, and after to use STAC to be able to search on this data, on this catalog. And the thing that we are really like that is really a game changer for us is STAC. Is very like very well-designed technology to be able to quickly manage to transform a STAC catalog in an X-array. So it's definitely better and easier to work with X-array than a STAC catalog. So here we have all the Landsat 8 data. So mainly we do not have a lot of data, and this is not the purpose, but here you are able to really scale if you want, like all the fronts, you are able to compute all the fronts on surface temperature. So for this data, for the Landsat 8 data, you do have all the metadata, and for example, we have all the imagery during 2017 until 2021. For each of these data, we do have a lot of different other information, like the cloud coverage, the projection, etc., etc. So, okay, cool. After, I'm going just to retrieve the data that is like really helpful for us. So for really need data with not a lot of clouds, it's definitely like difficult to work with clouds, as the satellite will not pass through clouds. So we are just going to use data with not so much clouds. Okay, so this is the data that we need. We have now our data cube. We have 24 different time, and we have all the band of Landsat 8. And that's where the magic happened. So now we are going to compute the land surface temperature based on the Landsat 8 imagery. And if we go through the land surface temperature function here, so we are using the code from we are going using a code from this so this basically the way to compute the land surface temperature for this type of data. So we are going to retrieve the good band, so the thermic thermal infrared band. And before that, we are going to create a cluster. And create a cluster is going to task coiled to create a cluster. So let's try. Okay, so here I'm going to, so it's going to task coiled to create this specific cluster. So I'm sorry, usually we have a cluster that is already there, and it's going to directly like connect to the cluster if you have one which is already alive. Here, as we do not have a cluster, it's going to create everything. So it's going to task. So coil is going to task after your AWS, for example, or GCP, or directly coil will create the cluster for you. So that depends if you do have already a provider of a cloud provider. For example, if you do have already GCP, you will just have to say to coil to connect to GCP. So if you have a credit from GCP, you will be able directly to use this credit from GCP with coiled. So here it's going to task AWS, our own account, the NetCarbon account, to create different cluster. And this cluster are, as I said, are the specific one that we have tasked here. Normally, I should be able to go to coiled. And the cluster will be here. So it's here. It's still pending, and after, when the cluster will be ready, you will be free to use it, or I will be free to use it, and after you will be free to try with your own account. And here I'm just going to connect to the cluster, so I'm able to see everything on the cluster. Oh, okay. So I don't know if it's going to work, as there is some environment issue, but don't worry, let's try, and after we'll find a way. So here I'm going to compute the mean land surface temperature. So the main idea is to say, okay, I have data from the land surface temperature during 4 years. So I'm going just to retrieve some KPI. The one that I want is like the mean during this 4 years of data. And after I'm going to do the computation. So what is interesting is that here, everything is in local. So it's in my own computer, but as I have connected Coiled and Dask, the computation here is going to be, it will be done not on my own computer, obviously, because my own computer will not be able to manage the computation. So all the computation is going to be directly with the cluster. And after, when the computation will be done, I will be able to retrieve just the data that I need and display it directly on my computer. So mainly what we really want to explain here, and what we really want to after to talk, it's three parts. The first one is that for us it was very difficult to find the relevant tool to be able to compute Earth observation data, because Earth observation data is like a very like it's not well known it's not well known, and there is like few packages that are open and that are available to be able to compute the data that we are working with. And mainly these packages are based on Python. And what is important is like there is a really good fit with Xarray. A lot of people are now starting to build new packages based on Xarray, because Xarray is like a very good way to have some data with the metadata, with everything. And what is like very important here is that Xarray is backed with Dask. So if you start working on Earth observation data, you will very quickly find Xarray as the relevant tool, and Xarray will be the good one because it's allowing you to be able to use Dask, and at the end to be helped by Coiled to be able to like push the limits of your computation. The second step, the second thing that we are really like we love pipeline. And I think there is a lot of people here that love pipeline because it's extremely important to be able to monitor like every step of your processing. We are just dealing with data, and when you are dealing with data, you really need like extract, transform, and load. And you have to be able to see all the log, to compute all the pipeline at the relevant pace with the relevant data. And to do so, there is a lot of tools. There is Airflow, for example, and there is Perfect. And honestly, that's a very good fit. We used to work on the Airflow in the past, but the way to manage to manage data is very tricky, because you have to store the data each time and to retrieve it after with the other libraries, and to store the data, to retrieve it, store the data, retrieve it. And what is very important here with Perfect is that Perfect is also able to use Dask and to use all these ecosystems. So when you are going to build, like, for example, the first function, the second function, and the last function, everything could be done in lazy mode. And you will just compute everything when you will task to task compute, or when you will ask to show the data, or to put the data on your on BigQuery, for example, at the end. So Perfect is like perfect to work with Dask and to work with Xarray and Coiled. And so that's something which is like really fitting what we are dealing with. And there is like a thing which is like very, but it's not Coiled is not an exception. So Coiled, Dask, and all this ecosystem, there's not an exception. So there is the very tricky thing, which is the environment management. So as you are dealing with your local host, and you are also dealing with remote computer, so you really need to have packages that fit together if you want to transfer data from one computer to the other. So that's the really tricky part, is really to manage to be like very strict on this point, to say, okay, I have two packages, I really need to have these two packages with the same version in the two computer, and how I can going to manage to be able to share the data between both. So that's the way to improve. That's something which is still difficult for everyone, but here it's like, I think the biggest challenge is really to spend time to be able to be sure that you are dealing with the good environment. And I hope that the computation is done. Let's just one thing here, as you can see, for example, the packages are not the good ones, so there is not a perfect match between the Coiled and my local host. So I was not able to do the computation. That's just because that's not the good environment. So I'm going to go through the good environment. But as you can see directly, it's like the tricky part is to be sure that you are dealing with the good environment. And what is the case? It's running without any issue, but you have to be sure. And normally, yeah, everything is okay. And in the meantime, if you have any question.
There's something you said there, and I see a question coming up. I'll read it in a second. There's something you said there about getting the right versions of everything. And we recently released what's called Runtime. And it has the entire package of all the kind of the get started, all the right versions of everything you need in one go. I can send that with this recording for people.
Okay.
I don't know if you use that. Marius is asking, what does the software param of Coiled param for cluster do then? Parameter, thank you. Cluster do then, does it not set the good environment in all workers?
So if I'm not sure if I catch the question, but here for us really like the part which is tricky, it's that the software which is here, it's something which is already built. So we spend a lot of time to say, okay, we are going to build a software. The name is going to be NetCarbon, and we are going to put these packages, etc., on this software. After, you push it to Coiled, and Coiled will create everything based on Docker, and so you can use directly pip, you can use Conda, you can use Docker. So as you really like what is fitting to your need, you are able to use it without any issue. But the problem is really like to have after the good version on your own computer, because here, everything that you see here, it's on my local computer, but the computation is done on Coiled. So you really need to have something which is fitting. So I just task here the computation. So as I said, everything is done in lazy mode. So you can do everything here. For example, rename, do some filtering, do some computation, but everything will be done in lazy mode. So you will compute nothing until you task here compute. When you will task the compute, it will create the graph. So all the steps needed to be able to retrieve your indicator, and it will send this graph to Coiled, and Coiled will after manage to create this graph and to do the computation. So here I have done the graph. I have sent it. I send the graph to Coiled, and Coiled and Dask will manage to do this computation.
Thank you. We have another question. Pavan Siligam. Have you tried to load the data from Coiled cluster directly instead as pushing the data to Coiled cluster from your local machine? If so, did you notice any performance improvement?
So that's a very good question, and that's something that we are already doing here. It's we are not retrieving the data from our local machine. We are just like, as I said, we are just like building the graph. So to say, okay, you are going to connect to this, mainly this database, you are going to do this step. And at the end is Coiled, which will directly get the item from the data. So we are not retrieving the data on my computer and first send it to Coiled, and after retrieving it, Coiled is directly retrieving the data, doing the computation, and pushing at the end the data to my computer. So here is the land surface temperature that I've managed to compute, and the most important part is after to visualize the result. So, okay, let's go on to Paris. Let's add a layer. Here it's a Kepler GL. It's like a software to be able to visualize geospatial data. It's an open source software from Uber that they have created to manage all the Uber that they have, because they have a lot of data and it was very tricky to be able to do it at scale. So they managed to create this small library. And okay, let's choose the good color map. It's going to be easier to understand. And let's add some satellite imagery because we are dealing with satellite imagery. Okay, so what do we have here? So we have here all the surface temperature during 4 years above Paris. So I'm just going to change the color, not based on the quantile. I'm going to really like base it on the quantiles to be able to really find places where there is some very high temperature and places where there is some very low temperature to really be able to understand what is like really going on in Paris. So based on this small computation, based on Dask and Coiled, I was able to compute a large scale of imagery, and after to just retrieve the insight that we really need. And what we can see very easily, it's here there is a really like some red rate value, and the red value are some very hot places. And what we can see here, it's Port de Versailles. It's near, it's in Paris, where there is a lot of like huge exposition, like for example, Vivatech was here. And as we can see, there is a lot of building. The buildings are very black. There is just few vegetation. And here there is some heat island. It's extremely easy to see, and it's extremely easy to understand that if you have to act now, you know where you have to act. And after, it's important to understand how you have to act, and that's the second step, to do some simulation to improve this. The other fact that we are able to that we can see here, for example, it's those two red area, and let's try to see what is going on here. So we have some train station. So as we all know, train stations are not the right place to add some vegetation. So it's usually some bare soil, and like is usually catching a lot of energy, and it's like storing a lot of heat. So there is some really like huge heat island, and that's the same here. It's train station. And let's go above, and okay, that's the same. So if we really want to act somewhere, also it could be here. After, it's not our, the purpose is not to give like the good or the bad, but just to understand what is going on in Paris. And obviously you have some like very fresh area. So if, for example, there is some really like some very high temperature during those few days, as we all know, the climate change will obviously raise the temperature, and it will raise the temperature a lot in cities. So if you want to find some places that are like maybe not good to stay, but if you want to have a bit of like fresh air, that's a nice way to find the good places, and maybe to improve after the places that you can improve. And obviously you have the water, which is like cold. So here you have in few minutes some insights that could be used. And if I don't know if you have some more time, but just to say that was just the mean. So that's the first insight, but it's also important to retrieve the standard deviation. Why? Because vegetation is like helping cities to have a temperature which is not like changing a lot. And when you have places like Port de Versailles or like train station, when it's cold, it's very cold, and when you are in summer, it's very hot. So the gap between those two values are very important. So when you are retrieving the standard deviation, you can see like the difference in time of area. And actually you can see easily places where it's very hot in the summer and very cold in winter. So it's a new insight, and is helping you to develop at the end the right tool for the right place at the right moment also. And the last thing, sorry, after, if you are like happy with the data, you know that you are able to work with the data, you just have to push it, for example, to BigQuery or whatever, to store it, to say, okay, I have my insights, now I'm going to work on these insights. one thing that's important also to know, it's a way of improvement. Maybe it's to have some good connector between BigQuery and Coiled, or to have some good connector with Dask and after GCP to store the data. That's some stuff that maybe would be improved in the future. But today, we still have to task Coiled to do the computation, retrieve the data, and after to send the data from our local computer to GCP or to BigQuery. And that's one step which could be very time-consuming, but it will change, of course, in the future. So I was very happy to present a bit like some Earth observation stuff and how Coiled and how Dask is helping us to build those type of insights. And obviously, I'm pleased to answer any question. And I think it's like the most important part. And sorry if I took a bit too much time.
Not at all. It's brilliant to see it. And I think everyone on this call, it's just really interesting, not even as a data scientist, but as someone living on this earth. I think it's super interesting. I don't see any more questions, but again, we'll send this recording and people can always reach out to you directly, right? With any question or thoughts or anything like that. Basile, this is fantastic. I see other people saying, thank you, Basile, very informative. On storing data, how do you store it so the lazy eval, lazy load part of Dask is still active? This is from Marius.
Okay, so when I have done the computation, it's like, so everything is done in lazy, and when you task compute, all the computation will be done, and after you will retrieve the data as a data frame in Panda or whatever. But when you task the computation, it will not be in lazy. You will directly have the data in your computer at the end. So after, this is why I'm retrieving the data, and after I'm able to display the data directly based on Kepler, because I have the data as a Panda data frame, so it's not in lazy mode. After, concerning the load part, so concerning the way to push the data, as I have the data as a Panda data frame, I am using Panda to GCP. So it's a package that is allowing people to directly push a Panda data frame to BigQuery. So that's just one line of code to say, okay, I'm going to push this data frame to this table from BigQuery and with this schema, etc.
And the following question is, and I think you partially answered it, but do you store as ZAR in BigQuery?
So that's a very good question, and that's something that we are working on today at NetCarbon. So today we are not storing it as a ZAR because we are really storing it in BigQuery. So in BigQuery we are storing directly the raw data. So each line is stored directly on BigQuery. But that's something which is like something that we are working on, is directly to do the computation in Coiled, and after to store from Coiled in ZAR to not BigQuery, but to Google Cloud Storage, to be able to directly have the data in Google Cloud Storage in ZAR format, and without the need to retrieve the data in my local computer. So that's, let's say, that's the next step. It's directly to store it in ZAR, because ZAR is like an amazing format in the big data, let's say, community.
And Pavani's asking, will this notebook be available to play with?
I think so, yeah. I think so. I'm going just to maybe to change some stuff, because as you can see, like we are dealing with the API of NetCarbon. So so I'm going to erase this part. I'm going to send to you, Ali, the notebook, and after you will have obviously to create your environment and to use Dask and everything around.
That sounds good. So let's try to include this notebook in the recording that we sent to everyone. Wonderful. That's great. Let me check one more time. I think we're good. All right, my friend, thank you so much. Really enjoyed it. It was fantastic. I'm always amazed to learn what people do with a large amount of data. Thank you very much. Take care.
Thank you. Thank you for your time. And if you have any question, feel free to send me an email if you want to know more about NetCarbon. And if you want to know more, obviously, about the EO world, I will be pleased to speak with all of you. Thank you. And thank you, Adi, for this opportunity to explain what we are doing at NetCarbon and to explain also how it's important to be able to really find some insights to fight against climate change altogether.